Scientists investigating the concentration of antibodies in the bloodstream of a patient following a vaccination. And the concentration, X, measured in micrograms per milliliter, is modeled by this differential equation, where T is the number of weeks since the vaccination was given. We're asked to find a general solution to the equation. So the first thing we do is set it equal to 0 and find what we call the complementary function. It doesn't matter what the right-hand side is. If we can find x such that the left-hand side is 0, that will obviously give us a solution. And then we'll find what we call the particular integral when we need to get 26. So we're going to I'm just going through the process here. You don't have to write all this down in the real thing, but let x equal a e to the kt. That means that dx by dt, when you differentiate this, you just bring a k down, so you get k e ka e to the kt. And then the second derivative ends up being k squared a e to the kt. And if you sub that into the left-hand side and then divide through by x, then you'll be left with what we call the auxiliary equation, 100 k squared plus 60k plus 13 equals 0. We solve for this, and this will give us our x. Okay, in this scenario, you definitely want to just be putting it in your calculator. It ends up being complex. K is equal to minus 0.3, or you might write it as minus 3 over 10, plus or minus 0.2i. And the consequence is that xcf ends up being, right, we need the real part. We got e to the minus 0.3t. And then the 0.2i part, you write, so it's a sine 0.2t plus b cos 0.2t. And just a little reminder where this comes from. So we've got our e to the minus 0.3t, and then you could write it as c e to the 0.2i plus d e to the minus 0.2i. It's just that, these contain imaginary parts. We want it all to be real. So then using Euler's relation, we can rewrite this as cos, sorry, there should have been a t in there as well, cos 0.2t plus I sine 0.2t. That's for that one. And then this one is very similar. We'll get cos 0.2t plus I sine minus 0.2t, which is minus I sine 0.2t. And basically, you can combine the constants in such a way that you can just write it as a linear combination of sine and cos functions. Okay, I'm doing it quite quickly, but also just trying to help you remember like why this works. Okay, so that's a complementary function. Now for the particular integral, well, we want to get it equal to 26. So I'm going to let x particular integral just be a constant. If you have any function of t in there, then, okay, when you differentiate it, you're going to get a constant. But when you kind of equate it, you're going to get a function of t here, which is equal, and then when you equate coefficients, you get 0. So actually, the particular integral is just going to be a constant. And then when you do dx by dt, you're going to get 0. So we're just left with 13 lambda equal to 26, and therefore lambda is 2. So x particular integral is actually 2. And we've got ourselves our general solution. We just add the two together. So it's going to be e to the minus 0.3t, a sine 0.2t plus b cos 0.2t plus 2. Right, now we're told initially there are no antibodies in the bloodstream of the patient. So when t is 0, x is 0, and the concentration is estimated to be increasing at 10 micrograms per milliliters per week. That's initially. So dx by dt when t is 0 is we're estimating to be 10. And using that information, we can get a particular solution, which we're going to need because then we're asked to find the maximum concentration after the max. But one thing at a time. We've got a general solution. Right, let's sub in. Sub in t equals 0. So we'll get 0 equals e to the 0 is just 1, and sine of 0 is 0, and cos of 0 is 1. So we will get 0 equals b plus 2. b is minus 2. Now I'm going to differentiate. Okay, I've got to use the product rule here. So if I differentiate the first function, I'll get minus 0.3 and then e to the minus 0.3t times all of this stuff. And when you differentiate the two, it just goes. And then we're going to be adding e to the minus 0.3t but times the derivative of this bracket. And in both cases, we bring out a 0.2. So I'll just bring out the 0.2 here and then write it as a cos 0.2t minus b sine 0.2t. Only thing is, I actually know what b is, so I might as well change it around. So I've got a minus 2 here, and then minus b, well, that's going to become plus 2. All right, so again, let's sub in t equals 0. So now 10 is going to equal minus 0.3 times minus 2 for that first part, plus 0.2 times a. That becomes 0.6. I've got 9.4 is equal to 0.2a. Divide by 0.2 or times by 5, however you want to think about it. A ends up being 47. And therefore, x particular solution is going to be e to the minus 0.3. I think this is worth writing down. 47 sine 0.2t minus 2 cos 0.2t plus 2. But actually, I mean, I like to write that down, but actually it said find the maximum concentration of antibodies at in the bloodstream of the patient after the vaccination. So that's going to be when the derivative is 0. So actually, that's what we need to look at. We need to find the time when the derivative is 0. So all I need to do is take this, write 47 here, and then set it equal to 0 for stationary points. And we can assume that the first one is going to be a maximum. It's going to be like increasing, then it's going to peak and go back down. So, okay, what we can do first up is divide through by the exponential. It's gone. And then I'm going to times through by 10. So this just becomes 3 and this 2. That is a really good starting point, I think. Now let's get it so they're on opposite sides. If we add this first term onto both sides, we'll get 3 times 47 sine 0.2t minus 2 cos 0.2t equal to 2 47 cos 0.2t plus 2 sine 0.2t. Let's multiply out the brackets. We're going to be turning this into a tan equation, so I'm going to get 143 sine 0.2t is equal to 104 cos 0.2t. Divide through, so sine over cos becomes tan, and then 104 over 143, well, let's just leave it like that. And then let's do inverse cos. So 0.2t, working in radians, remember, ends up being 0.61025. And we want the first value here. Divide through by 0.2, t equals 3.0512. You can find more values and sub them in, but because it's a negative exponential, it's going to be getting smaller. That is our highest peak. And then here, x is going to equal, right, this is why you did need the particular solution. Sub in your value of t into here. If I look at the first part with the exponential, this gives 10.127, add on the 2, and we get 12.1. So that is our maximum concentration, where is it, all the way back here, of antibodies after the vaccination. Then we're told a second dose of the vaccine has to be given to try and ensure that it's fully effective. It's only safe to give the second dose if the concentration of antibodies in the bloodstream is less than 5 micrograms per milliliter. So it wouldn't be at the maximum value, of course, but we're asked to determine whether, according to the model, it's safe to give the second dose exactly 10 weeks after the first dose. So actually, we just got to sub in t equals 10. This, in some ways, is a lot kinder. It's just kind of I guess, a slightly different application question. So when t equals 10, x equals, again, sub it into our particular solution that we found. Where would it go? Here. Okay, put it into here. And we end up getting 4.169. So this is lower than 5, and model therefore suggests it is safe. The only thing I would be thinking about is it on the increase? I guess it says to give the dose when it's less than 5. It's just if it then increases above 5, is that still okay? But in fact, it doesn't increase above 5. It continues to decrease. You could put in t equals 10.5, 11, and you'll see that is happening. So yeah, model suggests it is safe, and that is it. Well done.